Fine. Today's agenda is the most important agenda where we will be dealing with the circuit design using MOSFETs. Circuit design using MOSFETs. So we will begin with the gates. Okay. This and especially we are covering the circuit design using MOSFETs in complementary MOS technology, that is called as CMOS. I'll tell what is that CMOS and all. It is called as CMOS. Complementary MOS. MOS means MOSFET. Complementary means what? Actually we have P MOSFET and N MOSFET. Both are complementary to each other. Both are complementary to each other. Okay. And when we combine both the MOSFETs in our design, okay, PMOS and NMOS, which are complementary to each other, we call this combination as CMOS. Now you may ask, can we design circuits only using PMOS? Yes, it is possible. Can we design circuits only using NMOS? I don't want to use PMOS. That's also possible. But the most efficient way of designing the circuit is using both of them. Okay, we have to use both of them. So CMOS stands for complementary MOS or MOSFET. Complementary MOSFETs. So there are few thumb rules which we have to follow when we go ahead with the gates design. Okay, let us take very simple inverter or NOT gate. Okay. So let me tell you the thumb rules which we have to follow in almost all the CMOS related designs. So the first and foremost rule is there will be a imaginary line at the middle of the circuit, at the middle, that is imaginary. You need not draw it, though I have drawn it. Okay. I have drawn it only for your purpose. This is imaginary and this is called as demarcation line. Demarcation line. Above demarcation line, we will have P MOSFETs. So first you should know how to write the P MOSFETs or the notation or the symbol of P MOSFET. With the bubble, I have P MOSFET. Okay. Without bubble, I have N MOSFET. So the rule says that above the demarcation line, we should place the P MOSFETs or P channel MOSFETs. Below the demarcation line, we should place N channel MOSFETs or N MOSFETs. Clear? Then, it is generally taken that any system in general, okay, at the top we will give power supply. At the bottom we just ground it. I'm taking in general. Left hand side will be the input loop, correct? And right hand side will be the output. In most of the cases, we see this convention. You take any circuit, top we will have VCC, VDD and all. Bottom we will have ground. The same way, here also, we have VDD at the top, we have ground at the bottom, okay. We have inputs at the left hand side and we have output at the right hand side. Clear? Next. Now here this we can easily write. This is nothing but the gate terminal of the MOSFET, and source and drain. Wherever we write P MOSFET, the source will be near the VDD, drain will be the other terminal, and here when we write about N MOSFET, this is actually complementary of this. Source will be at the bottom near to ground, and drain will be having some higher voltage. So the fundamental thing behind this is source of P MOSFET should be at the higher potential or higher voltage. Source of P MOSFET should be at the higher potential. Source of N MOSFET should be at the lowest potential. You can say lowest potential of should be connected to source of NMOS. Highest potential should be connected to source of PMOS. Therefore, we are just doing this arrangement. Actually, you can tell drain can be at the top, source can be at the bottom. Yes, it can be, but you have to follow this thumb rule. Source of PMOS is always connected to highest potential wherever possible. Okay. In later stages, we will proceed with design. There you will get some doubts and all. We will clarify. Or in general, to keep in mind, all PMOSs, source at the top, drain at the bottom. All NMOS, drain at the top, source at the bottom. Right? Clear? Okay, next. We will short the gate. We have the gate. Actually, why it is like that? You can relate this to your basic working of N MOSFET or P MOSFET, which was discussed in the previous class. You just go back and see source of PMOS where it is connected, or if I had explained to N MOSFET, just check where is source of NMOS connected. Where is source of NMOS connected? It is grounded. It is grounded. Okay. And I had said PMOS and NMOS will do reverse. If you want to convert PMOS into NMOS, P will be replaced by N will be replaced by P. Positive voltage will be replaced by negative, negative will be replaced by positive. Okay. So positive will be connected to source in the PMOS. That you can verify later. Next, we are designing the inverter. Okay. We are designing the inverter. So this is the symbol of inverter. Using MOSFET, how we are designing the inverter is, we are shorting both the gates. Gate of PMOS and gate of NMOS shorted. Okay. You need not keep this demarcation line. I said it is imaginary. You can imagine it, need not draw. If you draw also, not an issue, you have to write demarcation line. Okay. But we just try avoiding demarcation line representation. So gate to gate is shorted, okay, and we give the input at both the gates. And drain to drain it is shorted. Drain to drain it is shorted, and we just take the output terminal from this common point. Drain to drain is shorted, and we take the output from that point. Then source of P MOSFET is shorted to VDD, and source of NMOS is shorted to ground. Source of PMOS is shorted to VDD, source of NMOS is shorted to ground. So theoretically this completes the inverter design. All the gates will be shorted. In later designs, later circuits we will see, all the gates will be shorted, all the drains will be shorted most of the time. We come to know one by one. Now, if you refer back the table which was given in the previous class, gate 0, gate 1, we have NMOS and PMOS. Gate is given 1, NMOS will be on, and gate 0, NMOS will be off. If gate is 0, PMOS will be on. If gate is 1, PMOS will be off. And tell why these things and all. Actually, there is mathematical equation for this. And during construction and working, we have seen it. Okay. So just apply this at the gate. So input, if I make input as 0, that 0 is going to gate of PMOS also, that 0 is also going to gate of NMOS also. Because both the gates are shorted. Correct? Both the gates are shorted. If I give 0, that 0 will come here also, that 0 will come here also. So now, just apply this table here. We are understanding how inverter works. We are understanding how inverter at transistor level works. We know inverter how work ಆಗ್ತದೆ 0, output will be 1. Or if the input is 1, output will be 0. This thing we know, but actually how it works, we are going a bit deeper. Okay. So if the input is 0, okay, gate of PMOS is getting 0, what it should be? It should be on. So let me draw equivalent circuit. The form of switch. Say this is VDD. This is PMOS. So when PMOS is on, we can say that the switch is closed. This is output. Okay, see, this is source. This is drain of PMOS. This is acting like a switch. When we say gate is given 0, PMOS is on, therefore I have represented PMOS with a closed switch. On, it is on, current is flowing. And input is 0, what about NMOS? On or off? Input is 0, NMOS is off. So when it is off, there is no current flow, or I can say that switch is open. So this is drain, this is source, and this is ground. Correct? CMOS is on, CMOS is off. Output is shorted to what? Ground or VDD? Output is shorted to ground or VDD? It is shorted to VDD. You can see here. That means current flows from VDD to output. Or output is nothing but VDD or 1. Correct? What about the other case? Actually, what was the input given? Input will be 0. What output we got? 1. Same case of inverter. We give 0, output will be 1. Now you change it. Give input as 1. Give input as 1. What about PMOS? On or off? On or off? Off. Off means open circuit. What about NMOS? NMOS. On. On means closed circuit. Now you just observe output is connected to VDD or ground? Ground. So what is ground actually? 0. So it is connected to ground. Or the answer is 0. Answer is 0. What input we have given? 1. So it is inverting. It is inverter. And it is inverting the input. Therefore it is inverter. But it is not gate. If you say 0, it will say 1. Okay. If you say 1, it will say 0. Therefore it is not gate. Understood? Next we will go ahead with the 2 input NAND gates. 2 input NAND gates. Those are getting sleep, things in water. So interesting. Don't sleep. One more rule which I'll tell now. The rule says that you take any equation, say y is equals to a dot b whole bar. Okay. Whole bar. The complementary MOS design or CMOS design, whatever we are studying now, we are studying the design using CMOS logic. This is CMOS logic. What is CMOS logic? Complementary MOS logic. What do you understand by that? We use PMOS and NMOS both. Okay. In CMOS logic, the question should have whole bar. Complementary whole bar. Question should have whole bar. Suppose question is not having whole bar. Y is equal to a dot b. If this is the given question, which gate is this? This. And this is NAND gate. If the question given design 2 input AND gate using CMOS logic, then first step what we have to do is we have to bring whole bar on it. Okay. So if I write only one whole bar, then actually I am changing the logic itself. The given question was AND, but I have converted it to NAND. So I am not designing AND, I am designing NAND. But my question is what are AND? I have to design AND. So now what is this? Now what is this? Now it is AND. What was the condition? Condition is you should have at least one whole bar. At least one whole bar. I have two whole bars, it's not an issue. I can continue. At least one whole bar should be there. Clear? One more important rule. This is the most important rule in CMOS design. Whenever I have dot, N MOSFETs should be connected in series. For dot. Whenever I have plus A plus B, whenever I have plus N MOSFETs should be connected in parallel. N MOSFET should be connected in parallel. Okay. If I have dot product, if I have dot in the equation, N MOS should be connected in series. If I have plus in the equation, N MOS should be connected in parallel. You just remember this much. Okay. PMOS will be just reverse. PMOSFETs will be just reverse because it is complementary design. So if I have dot, NMOS is in series, what about PMOS? Parallel. You remember only NMOS. Okay. By default, PMOS is opposite. If there is plus in symbol, NMOS is in parallel, PMOS is in series. Okay. So now we will design two input NAND gate. The equation is y is equal to A dot B whole bar. Whole bar is present. Just I will go ahead. Whole bar is present. I will go ahead. I have to take two P MOSFETs and two N MOSFETs. Why I have to take two P MOSFETs and two N MOSFETs? Because I have two inputs now. In inverter I had only one input. I had taken only one P MOSFET, one N MOSFET. But now I have two inputs. Okay. And just observe what is present. Dot is present. For dot, what I will follow? NMOS is in series. So two N MOSFETs I will take and I will place them in series. Already. Because I know dot product NMOS is in series. Okay. So I have dot, therefore I take two P MOSFETs connected in parallel. To take two P MOSFETs, connect them in parallel. You just don't know how to do parallel connection and series connection. So these are connected in parallel, these are connected in series. And here is my imaginary line. Don't forget that. P MOSFETs above imaginary line, N MOSFETs below imaginary line. Okay. Now, as usual, we have VDD at the top and we have ground at the bottom. Fine. Next, you tell me. This is gate. This is gate. Source plane. Source of PMOS at highest potential. source of PMOS has potential. Here, source. If this is source, this should be drain. Because MOSFET has two terminals. One if it is source, the other should be drain. Okay. And we follow the same convention. We will repeat the same. Source near the ground, drain near the edge potential. This convention we follow. Throughout our CMOS design, we will follow this convention. Okay. Next rule says that gate should be shorted. So if I take input, there are two inputs A and B. If I take input A like this, A input is here, and if I take B input is here, okay, the same gate or the same A should be given to gate of NMOS. So the common input, wherever I have common input, A is common input. So gate of this and gate of this both are shorted. Here I should give B. Okay. Here I have given A. Will A equal to B? B equal to. So this should be shorted to this. Or in complex designs, what happens? The connection chala bit slicker, design complicated ಕಾಣಿಸ್ತದೆ. Okay, so what we can do, alternate solution is, if you don't want like this, here I can write the same A. Here I can write the same B. But you should know that this B and this B are not different, they are same. In lab, whenever you do, you just connect it. Connect ಮಾಡಲೇಬೇಕು. ಬಿಡಾಕ್ ಬರೋದಿಲ್ಲ. Okay, so this B is connected to this B, this A is connected to this A. Or it is as good as shorted, I am not shorting it. And next rule says VDD should be connected to source of PMOS and ground should be connected to source of NMOS. And drain to drain connection I do, and from this point I will take the output. This is theoretical design of two input network. Telling you theoretical. Why? Because what will happen in practical design? Fourth terminal is not visible. The designing only using three terminals. Only gate, source, drain. Gate, source, drain. Naamne terminal ಎಲ್ಲಿ three sir ನೀವು ಕೇಳಿಲ್ಲ ನಾನು ಹೇಳಿಲ್ಲ. How many terminals MOSFET has? Four. What is fourth terminal called as? ಮೂರು ಹೆಸರು ಬರ್ಕೊಂಡಿರಿ. Three names are there. Body, bulk, substrate. ಇದು ತೋರಿಸ್ತಾ ಇಲ್ಲಲ್ಲ. They are not showing it. Actually, we need not show it. But if you want to show, you can show. No problem. So the fourth terminal will be here. This is an active terminal. This is an active terminal. Okay, so always the substrate or the body or the bulk, whatever you say, it is shorted to the source. It is shorted to the source. So ಇದು ಇಲ್ಲಿ ಹೋಗ್ತದೆ, ಇದು ಇಲ್ಲಿ ಹೋಗ್ತದೆ. Or in general, what we can say, the substrate or the bulk or the body of PMOS is connected to highest potential. The substrate or the body or the bulk of NMOS is connected to lowest potential. Okay. So this will go down. This actually we did not draw this in exam. I'm just showing you. So this is practical design, which you will definitely do it in your lab. Lab work ಮಾಡ್ತೀವಿ. Okay. But in exam, not necessary. not necessarily that I have to show these connections. So theoretical design, I said it is completed. In lab, you need to connect this gate to gate, this gate to this gate, and substrate connection. Now you verify whether this design is acting like NAND gate or not. NAND gate ತರ act ಆಗ್ತದೋ ಇಲ್ಲೋ verify ಮಾಡಿ. ಹೇಗೆ verify ಮಾಡ್ತೀರಿ? Same thing. The equivalent circuit will VDD. Okay. Here it is output. Then I have like this. This is equivalent circuit. Okay. ಇಲ್ಲಿ switch will be closed or open. ಅದು ನೋಡಿ ಹಾಕೊಂಡು. Let us take the inputs A and B both 0 0. A and B both are 0 0. Entry. A and B both are 0 0. Both are 0 0. P MOSFETs are on or off? On andre I will just short it like this. Fine. I have shorted it. What about NMOS? Off. So let them be open. Fine. What the output is connected to? Output is connected to what? Output is connected to VDD. So output is 1. Okay. Output is 1. Let us take another combination of input 0 and 1. A is 0, B is 1. A is 0, B is 1. Now tell me. A is 0. So what will happen here? This will be on. B is 1. So this MOSFET is off. Off on the other. Next. A is 0. Off. B is 1. Now check where the output is connected. Output is connected to VDD. Is off into E on it. Correct? So output is connected to VDD, therefore output is 1. Take one more input combination 1 and 0. Now check. A is 1, B is 0. A is 1. On or off? Off. B is 0. On. A is 1. B is 0. You confuse all this not. What the output is connected to now? VDD. Take one more combination, that is 1 1. Tell me. 1 1. 1 1. Both are off. Both are off. 1 1. Both are on. Both are on. Where the output is connected to? Ground. So the output is 0. Now check. Is this the truth table of 2 input NAND gates? Correct. So this design is behaving like 2 input NAND gate. This design is behaving like 2 input NAND gate. Okay. If the question given is 3 input NAND gate, what you will do? If the given question is 3 input NAND gate, what you will do? 3 inputs A, B, C. What you will do? One more P MOSFET simply takes. Correct? How the equation will be dot C whole bar. 3 inputs. Dot dot. Everybody dot is the end. NMOS is in series. So I'll take one more NMOS. I'll connect it in series. I'll call it as C. I'll take one more PMOS. I'll connect it in parallel. I'll call it as C. Done. This is the design of 3 input NAND gate. 4 inputs. Attach one more. Attach one more here. Attach one more in series. 4 input NAND gate. 5 input. Attach one more. Okay. Suppose I have the question 3 input AND gate. 3 input AND gate. Y is equals to A dot B dot C. Whole bar is present or not? Whole bar is present or not? Not present. If it is not present, what I have to do? I have to bring it. So how to bring it? I can't keep it like that because it will be converted into NAND gate. But I want AND gate. So double bar. Okay. Now you momentarily forget one whole bar. You forget that I have one whole bar. Okay. Keep in mind that I have only one whole bar. There are actually 2. But keep in mind that I have only one whole bar momentarily. So ಇದನ್ನ ಬರ್ಬಿಡ್ರಿ. ಏನು ಕಾಣಿಸ್ತಿದೆ ನಿಮಗೆ? 3 input NAND design ready ಐತಿ. Design is ready. But ಇದು whole bar ಐತಲ್ಲ ಇದನ್ನ ಏನು ಮಾಡಬೇಕು? ಈ whole bar ಇನ್ನೊಂದು ಐತಲ್ಲ ಅದನ್ನ ಏನು ಮಾಡಬೇಕು? Y is equals to A bar. ಏನಿದೆ? ಅದು ಬರ್ಬಿಡ್ರಿ. ಇದು ಯಾವ್ದು ಈಕ್ವೇಷನ್? ಇನ್ವರ್ಟರ್. So one whole bar ಇದ್ದರೆ ಏನು ಮಾಡಬೇಕು? Inverter. So you think that you put A dot B dot C ಏನಾಯ್ತಲ್ಲ A dot B dot C whole bar ಏನಾಯ್ತಲ್ಲ you imagine that this is Z. Imagine that this thing is Z. So ಹೆಂಗೆ ಕಾಣುತ್ತೆ ಅಂದ್ರೆ Z bar ಕಾಣುತ್ತೆ. If this is Z bar. Correct? So A bar is Z bar is ಯಾವ gate ಇದು? Not gate or inverter. So for this whole bar, extra whole bar, what I do, I will connect an inverter at the output of this. Then output ಬಂದದಲ್ಲ ಇಲ್ಲಿ ಇದರ output I will connect an inverter. I will design an inverter. This is my inverter. Source, drain, source, gate. This is my inverter. Output of this 3 input NAND I'll give as input to the inverter. ಇದು ಏನು ಮಾಡುತ್ತೆ ಹೇಳ್ರಿ? You tell it 0, it will make it 1. You tell it Z, it will what it will do? Z bar. ಇಲ್ಲಿ Z bar ಆಗ್ತೈತಿ, Z bar ಬರ್ತೈತಿ. So output I will get here is A dot B dot C. What output I get here is A dot B dot C. Whole bar I get at this point. That is given as input to the inverter, so that it again inverts. And I get the output A dot B dot C. Now what you have to do is, based on the same concept, you design 2 input NOR gate, okay, 3 input OR gate.